Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre, with me is Z. Today we have some topics around exploit mitigations and kernel sanitizers coming to Windows and some other research. But before that, Z will get into this week's Spot the Vuln.
Yeah, and unfortunately, this is the only Vuln of the week, I think. Oh, yeah, this week was kind of rough when it came to or trying to find any Vuln write-ups that were slightly interesting. We ended up dropping one that was I was going to put it on here so we'd have a Vuln, but very straightforward Stack Overflow. Not actually interesting in like any way. Anyway, for the Spot the Vuln, fairly straightforward issue as long as you're already familiar with it. What we've got here is an int length. So for those of you listening, we've got a primary method here is this process data. It just takes this int sock, kind of saying it's got the file descriptor for a socket coming into it. From that, allocates a buffer, has an int length, I just have a function here, get data length, which reads it from the socket, giving you the idea that, hey, this is attacker controlled, it's just reading it from the socket. So you've got an int length, does a little length check if length is greater than the maximum length. The buffer I mentioned earlier is just a stack allocated array of max len. Return -1 if it's too big, and then just get data passing in that sock, the buffer, and the length being read. There's also the function signature showing that the length going into get data is a size t, so implicitly that integer is going to get converted to a size t. Size t being unsigned, length being signed. If you give it a length that is negative, that when it becomes a size t is going to become a very large number, leading to just overwriting the actual buffer when it does copy in the data. It does assume it's not using, so something like if it just does a read, that should actually check if you own all, or if you can write to or have allocated all the memory pages it's going to try writing to, so -1 probably won't work there. Uh, but assuming like get data does some sort of like buffered reading or any sort of stepped reading, you should be able to get an overread out of it. But yeah, it will depend a little bit. That is why I didn't just do a read call there. It's on most modern systems. Read call won't work. But yeah, it's just that having the integer and turning it into a um turning it into a unsigned value. The basically just type confuse, or not really type confusion, integer signedness issues. Rudimal mentions -1 could work if you could just apply less data, close the connection or something. Well, that would still, so if you call read, just like the read syscall with a large length, it's not even going to try reading that much data yet. It's just going to look if it can write, like if those pages are all mapped or whatever. Um, I'm not sure what exactly the check is there, but I initially wrote this using read, and then gave it a try, and it just didn't work at all. It didn't overflow anything. It just died earlier. So I assume something's going on there. I didn't dig into what the cause was, but obviously I think a lot of us have seen this sort of bug, especially when you do have that sort of stepped reader that you could just close the connection after a certain period or whatever. So that's why I just called it get data, as a kind of emulating that sort of process where just they implement their own kind of reader.
All right, cool. So we'll get into our topics, and we'll start off with Microsoft putting out a post on kernel sanitizers that have come to Windows, the Windows kernel, as well as the secure kernel in Hyper-V, which is fairly interesting. Seems like Microsoft is catching up a bit and making some ground in the kernel security space. So, SAN, or address sanitization, for those who might not be familiar, is an instrumentation where a shadow mapping is created to keep track of memory states. And allocations, frees, etc., will keep track of whether or not a particular address is valid, and then memory accesses are instrumented to check against that shadow mapping to make sure that an access is valid. Whether those be and it'll detect invalid accesses, whether those be like out of bounds accesses, use after free, whatever. Very useful to have, especially for things like fuzzing and the like. though not too good to have for production builds, especially in this case. Among some of the technical details Microsoft goes into here, in Windows it has about a two times slowdown in performance, so it's a pretty heavy cost to pay on the performance side of things.
which
But
I
it can
think
be
is
very
pretty
useful for trying to catch
similar
bugs.
to what like Linux has it at too. When you do KSAN in Linux, I think it's something like a 2x slowdown also.
Do you remember if that was for outline or inline instrumentation?
Oh, default I think is inline, right?
No, I think default's outline. I think you have to switch it to inline.
Okay.
Maybe inline's a
Um,
bit
you
better.
know what? I don't remember to say for sure. I thought default was inline. Whatever the default is, I believe that's where I'm getting the 2x number. I didn't even look this up beforehand, so I just might be completely off anyhow. So
Ah,
I
fair
don't know.
enough. It was mostly just point of curiosity on my side.
Yeah, I mean, it's just KSAN has a performance hit. No matter what, like even when we're talking about user land ASAN, there's a performance hit from this. You're instrumenting every load and store, and it's doing these checks on every single one of those. You're going to have a performance hit because of it. Um, but it is really useful, like you said, and you kind of glossed over it, but it hits like it can detect the use after free. So it can detect that and induce a crash. 'Cause with fuzzing, especially, the value of these sanitizers is they can induce a crash. So you know, hey, this is a bug that normally it wouldn't crash unless you have just the right conditions set. But they know it's a bug, so they can induce crash. You can also, not sure about Microsoft's like KSAN implementation here, but like ASAN through like Clang. Using that, you can also tell it not to crash and keep going, just print the warning or whatever, so it doesn't have to crash. But either way, it's able to detect that, make it known, especially to fuzzers, that something's gone wrong. Like use after free is not, in many cases, it's just not an obvious bug without something like this. So it just makes it a lot easier to detect these sort of memory or some types of memory corruption bugs.
Yeah. Now they do go into a good bit of the technical details here on how they implemented it. Part of the reason that it took so long for it to come in is because Windows has some unique challenges when it comes to instrumentation like ASAN. For example, something we've talked about a lot before is the fact that kernel functions can call into user mode through user mode callbacks, and that kind of messes with like how ASAN can keep track of the shadow mappings. They talk about how they work through some of that there. Um, I won't go too much into the weeds because it's very specific to Windows, but yeah, there's some cool information here. And as I mentioned earlier, not only is this in the Windows kernel, but it's also made its way into the secure kernel for virtualization-based security, as well as Hyper-V itself, which are obviously pretty uh, like nice targets for attacking. So it makes sense from the defensive angle that they would want to have instrumentation there as well. Towards the end of the post, they talk about some results. Unfortunately, they really don't go into specifics here. They do have a pie chart demonstrating the more common types of bugs that they've seen so far with the SAN, with out of bounds access being the top at like 70% of findings, followed by type confusion and then UAF. Nothing very surprising though. We've seen similar charts in like Google's posts, for example. They look very much the same way with the same breakdown of bug classes. So I figured I'd
Yes.
call it out, but it's not surprising.
Yeah. I will also mention Rudimal just asked in chat, how does inline versus outline differ? Since we were just talking about that very briefly and just kind of assumed people would understand. Inline, it basically just has to do with how the instrumentation happens. If it's inline, it's instrumenting like every time the load or store happens, it's just adding those instructions there. Whereas the outline instrumentation will add a function call that does it. So it'll inline will have like a larger binary size but better performance, whereas outline will have to make that function call every single time, having worse performance, but it will have a smaller impact on the actual binary size. But yeah, coming back onto the KSAN here, I'm unclear if Windows is actually providing builds of the Windows kernel with KSAN. I did hear from someone that they did run into some KSAN warnings on like a Windows preview or insider build or whatever. So it sounds like they might, but when I'm reading just this, it does sound a little bit like it's just like they're enabling the function calls in the kernel so then your drivers can start using it. which is still a benefit, but it would be really nice to see the Windows builds. And I'm hoping they do have the Windows builds, and I'm just misunderstanding part of this. Because they do just talk about like the KASAN on drivers versus KASAN on NTOS.
They kind of mentioned that, like in this section here, Microsoft generates special builds of Windows called Mega ASAN builds that produce fully bootable images
Sure, but
by using
they
these builds for
say
testing,
we
fuzzing.
produce elsewhere they say, we produce the internal Mega ASAN builds with all of these.
Yeah, yeah,
Uh
that's fair.
that's where I'm not sure if they're actually writing those out, because this would be huge for anybody doing fuzzing. At least I imagine it would be for doing fuzzing against the Windows kernel. Just because it can now detect those sorts of bugs that otherwise are just a little bit harder to actually realize happened without actually having the crash result of it. Of course, it would also make it easier for malicious actors to find those same bugs, so I could see them not doing it. It is something I'm unclear about. Because even when they're mentioning like the hypervisor ASAN, like I'm not sure how that really ties in here. If that's just like, yeah, we're doing it. At least the secure kernel one, they mention you can hook in with that with the secure kernel app. So fair enough on that side. Hyper-V, I'm not sure if they really have anything that's similar at all. Um, so I'm not sure if they're just going to provide Hyper-V builds that have KSAN built in, all that instrumentation, or how they're exposing that. It's still nice to see, but yeah, as we're talking about here, I'm not sure what this looks like in terms of what we're actually getting from it. The
The
ideal
way I
case
read it is it's
is,
more for Microsoft's internal fuzzing and stuff like that. But
which then it's really surprising they didn't have this before. Um, I if it is,
well, like I said, there was
well,
some unique challenges, right? Like it's kind of similar to SMAP. I don't remember if we talked about this on the podcast back when it happened. But back when it was announced that like SMAP was coming to Windows, but it was only coming to like very specific. I forget what the name of the mode is, but it only impacted like some of the kernel because there were just so many places it would call into user mode and SMAP would break it. Windows has a lot of those like unique challenges because of how it's architected compared to other operating systems.
yeah, and the
So
legacy support too.
yeah,
SMAP
that too.
really on SMAP and legacy support. I mean, so many drivers just assume that access.
Mhm.
And I guess for those of you unfamiliar, SMAP is supervisor mode access prevention. When you're in kernel land, it just doesn't let you access the user land pointers.
Not without going through special channels of like clearing the AC flag and stuff to mark your intention, basically.
Yeah, you
Um,
have to tell it like I'm intending to hit user land stuff or to look at this user land stuff before you can, and then when you're done, you flip that back. Usually that's done through like a function that always does it rather than implementing that yourself, but
yeah. So there's some nice specific details here. It's nice for Microsoft that they're getting the ASAN into those components. Like I said, like when you're talking about virtualization-based security and Hyper-V, especially, they are major targets. So it makes sense for them to try to get ASAN there. And yeah, it seems like they're catching up a little bit. Unfortunately, though, beyond some of the implementation specifics, they don't really go into a lot of detail on the builds and the stuff that C was talking about. So
yeah,
can't
it's
can't really talk about that too much.
really nice to see though. Like I said, especially if this is something that they're going to have on their kernel and builds available for that. I feel like it's a big move for like just fuzzing the Windows kernel in general. Like I have to imagine a lot of bugs will be discovered. I mean, even having it just on drivers and stuff, it is still going to be, I think, a pretty big step. I don't do the Windows kernel research, so maybe somebody will chime in and be like, no, we've got whatever already, and this is no big deal. But to me, it seems big because at least doing a lot of the Linux work, I mean, ASAN and KSAN are major players in any sort of fuzzing campaign that I've done over the last several years.
Yeah. All right. So getting into some mitigation stuff, we have a post titled "Fun with Gentoo" about shuffling ROP gadgets. Z, I'll let you get into this one.
Yeah, this is again, since we don't really have vulnerabilities to cover here, the idea that they're pitching here isn't exactly novel. I guess they actually mentioned, yeah, the basic idea is not new. Anyway, OpenBSD has been doing it since 2017. The really core idea here is, what if at link time, if we just linked all of the object files in a random order, the result of that would be a binary that isn't completely randomized, but usually, you leak a code object for whatever module you're dealing with, like a shared library. Leak a code pointer anywhere in there, and you can figure out the offset to every other function. Whereas doing this sort of linking with a random order, you would no longer get that. You would have maybe a few functions that are in like the same file or whatever's for that object, but you wouldn't have you wouldn't have the offsets to all the pointers everywhere in that module. Um, it's a neat idea, so I figured I'd at least bring it up here. It does make ASLR, it does make the exploits less portable, is effectively what it does. You write an exploit on one system, offsets may be different on another, but it depends on somebody actually building their own code. So if you're just using a download from somewhere, like if everybody's using everybody on Ubuntu might be using everything off of like apt or whatever repository they're getting it from, it's going to be built the same way every time. It's not being randomized at that stage, so it decreases portability, but it depends on people building things, which just kind of limits, I think, the impact of it. But I thought it's also fun just to talk, or reminded me a little bit about the shuffler discussion we've had, which way back on episode 13, we talked about shuffling and like some of the different mitigations that exist, that take this idea a little bit more seriously. So the title here is, why don't we just shuffle those ROP gadgets? The idea with shuffler, so one of them is actually called like shuffler. The other one that I tend to remember was zipper, ZIPR. And the way those work, shuffler would like randomize the memory layout and where all your functions were. I think it was just like a function level shuffling. I do have my notes here actually. But it would randomize the functions and where they're laying out every few milliseconds. So like you'd get a address leak, you'd get your info leak, and you have a few milliseconds before your address leak is no longer useful because it's already reshuffled memory. Of course, that has performance hidden. We're like probably never going to see that actually happen. Zipper stood out because it does instruction level re-randomization, scattering all the instructions around. I forget exactly how that one worked. It had a bit of a weird system, but effectively it did what the label says. It would scatter instructions around, so it wasn't executing just linearly. Those would be more effective than this. Oh no, I was just reminded about kind of shuffling or these sort of shuffling mitigation, so I thought I'd mention it here, but uh yeah, I don't know. I mean, Spectre, have you need to deal with any sort of shuffler in play or even just fine-grained ASLR?
Not really. I was just about to get into that though. Like, this is pretty coarse grained as far as ASLR goes. Like, obviously, it's more fine grained than ASLR on the entire binary, but it's still uh, like some of the stuff we've seen before was at like the function level and stuff like that, which would be a bit more effective. I haven't had to deal with it. Uh, there was some interesting discussion involving some people I knew that were talking about this sort of thing. I don't remember if it was spawned off of this like uh, this post specifically, but prop gadget shuffling is kind of a weird thing where it can definitely be annoying to attackers and hit like the reliability or the portability aspect of it. On the other hand, it's also going to be mostly useless unless the like bug you have is garbage. Any solid bug is going to be able to get around. Like it's going to be able to find ROP gadgets dynamically, or it's just not going to use ROP. If something like this takes off and makes ROP annoying, it's just going to shift the meta to doing more like data oriented type attacks. So
Which is where
um,
the meta is kind of going, anyhow.
yeah. So there was some talk about like how effective and how worth it this would be. Given the fact that I don't think you would have a lot of drawbacks to doing this, it might be worth like doing it. Because I don't think you're really going to have a ton of overhead with this unless I'm wrong.
There's
Uh,
no overhead from, well, I mean, build time, you maybe have a bit of overhead from the shuffling of that. That said, like I was mentioning earlier, it kind of depends on everybody building their own software.
mhm.
Like anybody that's using a downloaded piece of software, download library, isn't
Which
getting
just
this
isn't really
sort
going
of
to happen.
protection. So
Yeah.
either like, and if you go and um, default, like every build does this randomization, um, like I guess that could work, but there's already a reasonable chunk of differences across like different platforms that I feel like this just wouldn't be worth it, especially because this also kind of breaks what's it called? Reproducible builds. I think there's a better name for that. I can't remember what it is. But just the idea of being able to so somebody puts out a binary, um being able to reproduce their build and getting the same hash to know like they really are building this binary the way they're telling us and not including anything extra in the binaries, being able to spot check just the random binaries you use because it randomizes that the hash will change and it will be different. So
Yeah.
it does kind of break that, which there's an argument to be made as to why build reproducibility doesn't matter. I'm on the side of kind of preferring it, but there are arguments against it too. So perhaps that to some that's just not a very strong argument.
Yeah. I guess my main argument against this though is that pretty much any scenario where you're able to defeat the more coarse grained ASLR, you're probably going to be able to defeat this too.
Yeah,
So
this
it's
one,
probably not really providing a lot on the defensive side.
yeah, this one especially. Fine grained ASLR at like the more the function level does get more challenging, but this doesn't break it up anywhere near enough.
Hmm.
Because your objects are generally going to be at like roughly a file level. Um, Odds are you're going to have the gadgets inside of a file to use. Like unless you break it up, so like every file and you go the Java route, every file its own class, every file its own function or something, which would be really annoying to read that code. Yeah, I kind of agree with you. Like I don't think this is really worth doing. I mean, it doesn't hurt that much, but I don't think it adds much. But I will say it's still a great post in terms of just thinking about things and recognizing, hey, there is this simple solution. This is this simple thing. And yeah, we're probably not going to see it. But they're right. Like it is a simple thing that can be done without without any runtime performance overhead. Like it's great to be thinking about that, and I mean, spawns a little bit of discussion.
And I guess one thing I'll call out is in their conclusions, they kind of state like, it's not a silver bullet, but it should raise the bar in particular for remote attacks. So for services that you're running remotely that are, accessible to WAN, something like this might make sense to do. Just as like,
Fair call.
it's basically free and simple, and it could impact the remote attackers more. So that's fair. That's a fair point by the post there, but. Yeah, in a lot of scenarios, I don't think it's going to do too much. But like you said, it's simple, so it's doesn't have a lot of drawbacks on the performance side. So you can do it if you wanted to.
Yeah, and in
I
fairness
just
to the
wouldn't rely
post,
on
like
it as like a strong shield or anything.
yeah, it does add a little bit. It adds that I mean they do mention there the single pointer leak gets you less. It does do that. I don't think that really matters a ton, but especially in some setups, it actually could make a decent difference. But yeah, on a whole, I guess I just give this a meh. Like it, you could do it, you cannot. it's not making that much of a difference, I think, in terms of exploitability or anything.
Yeah, I'm in the same boat. All right, so getting into our last topic, we have a paper on automated detection of exploit primitives for heap vulns. And the paper is centered around a tool they've worked on called DEPA, which they evaluated against CTF programs. To clarify, by exploit primitives here, they mean things like arbitrary write and arbitrary address jump or code exec. They seem to have like recoined a few like commonly used terms. I'm not sure why, but yeah, when you see arbitrary address jump, that's basically what they're talking about. It's just like a IP hijack. Um, we've talked about some similar research to this before. I think it's been a long time though. Like it was on our earlier
Yeah,
episodes. I
it
want to say in
was.
like the 20s.
Yeah, I think the last time we talked about was probably that Kobe paper, the kernel out of
I was
bounds.
trying to remember what it was called. Thank you.
Yeah, I think that was the last time we talked about this sort of thing. Although this takes a rather. There are some similarities in the approach, but it does a couple novel things here.
Yeah. Um, so the aim of this paper, as opposed to like prior research, is to handle event loop driven stuff a bit better. So say like a server or something that would listen for clients and incoming data. But the heart of their plan and what how DEPA works is looking for functions that they tag as primitive crucial behavior or PCBs. So their DEPA setup consists of two steps. First, they identify and find PCBs through static analysis. And then they use that static analysis to generate some templates and fuzz the program to assess whether or not they can get an exploit primitive or not. So, another hybrid approach combining static analysis and fuzzing, which is pretty popular and it works pretty well here, I think. Though I'll get into that a bit later. For their PCB analysis, they use symbolic execution with anger, and then they lift the binary to vex IR and identify things like allocations, frees, and memory options like loads and stores. And they do pointer dependence analysis, where they basically build a dependency table of operations on the pointer and try to determine, what primitives you could potentially get from that, like a what they call an arbitrary address write or just an arbitrary write. So, kind of a cool idea. Toward the end, they talk about the results. On 10 out of the 11 CTF challenges they tried, DEPA was able to identify an exploit primitive with various bug classes. I'm just trying to bring up the table of where that was for those who are watching. Yeah, here it is, I think. So, yeah, it worked pretty well in the CTF challenges that they talked about. As usual, when talking about these papers, though, and especially in this case, there is a very limited and biased sample size here. It's only looking at CTF challenges and only 11 of them. And CTF challenges are probably going to work a lot better for tools like this, as primitives are generally more obvious and contrived, which they kind of allude to in their conclusions. They talk about how DEPA couldn't really do real world programs as is because the constraint solving of anger just can't handle complex programs. I think it like runs into state explosion and stuff like that. So they say that's left for future work. Nonetheless, even though it is maybe not very practical for real world applications at this point, I think it is kind of an interesting approach. Combining the manual analysis with fuzzing, we've covered a good amount of papers that do this. It has been a while though. Something I like about it is by using both, you're kind of covering a lot of your bases. Whereas static analysis might be subject to more false positives, real live testing and fuzzing should help filter out things like that. And in general, you're kind of pulling strengths from both approaches. So
Yeah, this
I
does it starts to approach what feels like a bit more of a human methodology in
yeah
that they're taking the time to look at, what they call the primitive crucial behaviors. Those simple behaviors, just here's where an object, it dereferences a pointer to the object. Here's where it reads or writes to the object. Taking a look at those, and then you still have to provide it the actual exploit primitive, like where you've got a vulnerability. You have to provide that, doesn't try and find it. Um, but it takes a look at those other things, which is not really exactly the same approach like a person would do. Like you probably want to look at every single crucial behavior. There'd usually be some sort of like pruning that's going on mentally, at least as you're thinking about what the potentiality is for like your overflow use after free or whatever. But it's still an interesting approach to come in here and try and do that analysis. And then taking the human work, the exploit that comes in, merging these into something and kind of doing a little bit of fuzzing, which when we have covered like the Kobe paper, that started off where you gave it the vulnerability and then it would just fuzz that and figure out what it could do from there. This definitely feels like it has more potential to discover some of those that require some different structural changes. Like you need to do certain actions first. So when you need to groom or spray a little bit, um, it's able to at least start to detect where that might happen. There are definitely, spectral array hits some of the limitations on this. I mean, when you look at this table of like the primitive crucial behaviors they found in it, they have these different CTF programs. It's like they found one allocation in almost all of these, except for the one which had two allocations. That shows you that like it's not doing a lot when it comes to actually or I mean it is doing a fair bit, but like it's not finding or dealing with a lot of primitive crucial behaviors here. Like these are rather simplistic programs, and that's true with a lot of CTFs. They kind of have an idea of the exploit strategy they want you to use, and they're guiding you along to that.
Yeah,
Oh,
you're kind of forced into a particular path of the challenge designer in a lot of cases. So that's why, like, it's maybe not a great measurement of like testing this tool, because your primitives are going to be a lot more obvious where the challenge is designed around it.
yeah. Although, in fairness to them, like in theory, this could be applied better. They kind of put the bottleneck as being on anger and its ability to do some of the symbolic execution. I mean, it is just generally hard to do. Like, if it's trying to track all of the primitive crucial behaviors in a large program, like that is a lot to keep track of. There are going to be a lot of objects with like just pointers being dereferenced and things happening there. Like, there's just a ton going on that it's trying to track. Nonetheless, the approach, at least, it's feeling a little bit more human. It feels weird calling like, yeah, this is a more human program or whatever.
It's a more
But yeah,
deterministic approach, is how I'd put it. It's not like relying on luck as much as some of the other papers that we've seen, leaning more heavily on the fuzzing.
well, I mean, it still needs the fuzzing though.
It does, but it's also adding more of like a deterministic and methodological step into the process. So yeah, I mean, like I said earlier, it is nice to be able to combine fuzzing and the static analysis in that. I said earlier that you kind of get the strengths from both, but you also it's a two-sided blade. You also get the drawbacks of both. Particularly on the constraint solving side of things, which is why you have the problems with state explosion and stuff. Um, but yeah, I mean, there's some things I like. For one, it focuses on primitives, which we like to talk about a lot. And this idea of like primitive crucial behaviors, I thought was kind of neat, modeling primitives in this way to find them. But I do wonder how well it would work in non-contrived scenarios. Even if like the state explosion wasn't an issue, and you could just run this on regular programs and like it would work how they want it to. I wonder how effective their identification of those PCBs would be. Hard to say though.
I
It's
also
just
wonder what the time frame was because they don't have timing here, like how long anything took.
that's very true. I didn't even think
Um,
about that.
that was another thing. So, I mean, yeah, I know that's kind of just dependent on anger, but like that is another aspect that I feel like wouldn't scale very well.
Potentially, yeah. It's hard to know without the data. Which makes me wonder like why they didn't include that. Because now that I think about it, a lot of the past papers we've covered, they say on their graphs or whatever like this was after a week long campaign or something. But yeah, I don't remember seeing that. Oh, they do
They do
say
include,
fuzzing
well,
was conducted for 2 hours under the case with the template. Okay,
yes,
so
but
they
that
do have
was
some info
the fuzzing aspect. I'm more wondering about the analysis side of things because the
for
fuzzing
sure.
is just keep running it for more for a better chance, more results type deal.
For
I
sure,
mean,
yeah.
granted, they do fuzzing a bit differently here with template based fuzzing. Well, I guess they compare template fuzzing versus just random fuzzing, but yeah.
Yeah. So, wrapping it all up, I think there's some cool ideas here. Unfortunately, though, like a lot of the past papers we've seen that rely on symbolic execution and constraint solving, I don't really see how this could be used in real world anytime soon. A lot of those past projects just kind of didn't really go anywhere because it's a really difficult problem that seems to not have like it hasn't been solved for a while. So yeah, we'll
Yeah,
see,
I
but I
mean,
doubt we'll really see this being used in real world.
yeah, I mean the thing is, it's a research paper. This is something for somebody else to come and be like, "Oh, here's how we can build off of this." It's a stepping stone. It's not the end result. So, I mean, yeah, we're saying, "Oh, this isn't real world or isn't prod ready or whatever," but that's not the point of research, and still have to give him props for doing it in the first place.
All right, so that's all of the full topics that we have for this week. We do have some shoutouts we want to go through. So up first in shoutouts, we have a post by Cloudflare called "Arm to Boot" about ARM secure boot chain and some of the improvements that have been made to that. There's not a lot there in terms of the stuff we typically cover with like security. I mean, it is based on trying to architect the bootloader and the boot chain in a secure manner. So there's a lot of good background info on like ARM Secure Boot and how that process works. So I think it is a very cool post, especially if you're interested in, that firmware level, like trust zone and stuff like that. There's some nice diagrams and some good information here, but there's not a specific vulnerability or anything like that. It's mostly just talking about how it works. So if you're doing some research in an area like that, this could be a very valuable post to you. But yeah, just not anything we could fully cover with in terms of like vulnerabilities or anything like that.
Yeah, that's kind of what I saw with this one is there's just a wealth of information here, but it is all that kind of background, fundamental information you'd want if you're going to start targeting something like this or want to understand it. Looks super awesome. Cloudflare usually does these really good deep dives, so figured we'd give
Yeah.
it the shout out.
Yeah, and part of the reason it's being covered by Cloudflare, for those who might be a bit surprised, um, like attestation and secure boot is very important for cloud stuff. It's basically like the heart of cloud security, so that's why the cloud companies care so much about it. Cloudflare in particular, so that's why they like putting out the research like that. Our next shoutout is from GitHub Security Blog, and it's about a Mali vulnerability that was put out for pwning Google devices. Um, the title is "Pwning the all Google phone with a non-Google bug." Uh, Kind of the like implication there and why that's a bit funny is like the Pixel 6 moved away from uh like they basically run their own SoC, although it uses Mali, so that's kind of what they're hinting at there. We didn't cover this because it goes very specific and in depth into like Android and GPU stuff, and it would be kind of difficult to cover, especially in an audio format. But if that is an area that you're interested in, you like the like very nitty gritty low level GPU stuff, that post is there, and it's a really good post. So we wanted to shout
Yeah,
it out.
that's this is I was saying at the start of the episode, didn't really have any ribs. This is probably the closest thing to have mating or to having made the episode. But kind of like for the same reason we sometimes don't cover certain Windows kernel bugs. Sometimes the bug just is you don't have a lot of takeaways that apply anywhere except right here, or, that component or whatever. And it's just like it also just takes us a long time to parse some of those when we can't just apply knowledge from elsewhere. But yeah, I mean, from GitHub Security Lab. So again, he do a lot of really great posts. I know we've covered some from this is from Manumo. So we've covered his posts before.
Yeah. Lastly, we have a bit of a self promotion. I put out a AMD SP firmware loader on our GitHub account. This is a binary ninja plugin. So I've been doing some research on the AMD PSP platform security processor, which is kind of why I was geeking out a bit about the Cloudflare post, because AMD SP actually uses ARM Trust Zone technology in a very similar architecture. So yeah, I put out a binary ninja plugin that'll like load PSP firmwares and set up the correct address layout and everything like that. It was something I was working on for personal research, but I thought it might be useful for some people out there. There's very little public research on the PSP, which is part of why I'm doing it. I found it very interesting. So yeah, I thought I'd shout it out, but yeah, it's probably not going to be too interesting to you unless you're doing like PSP research or that area. But I figured I'd mention it. So yeah, that's all the shoutouts that we have for this week, though. So unless you have any last minute parting thoughts, see, we'll go ahead and wrap up the episode.
The one parting thought that I will kind of toss in here is, on this episode, we didn't dive into a lot of, or any vulnerabilities. Let us know what you thought about that. Like, if you preferred us having some of these more discussional topics or not, I'd appreciate getting some feedback on that and just over our normal content.
Yeah, for sure. Because yeah, it's hard to gauge like what exactly people are interested in. The more discussional stuff can be fun, but yeah, it'd be good to take a bit of a survey and see what people are interested in. So feel free to drop by our Discord and leave some of the feedback on that. And the Discord links are in the description or also in the chat for those of you who are with us live. So yeah, as always, thanks everyone who tuned in. Past episodes are also up on YouTube. Spotify, Apple Podcasts, and more. And yeah, once again, if you want to join our Discord or check out our Twitter, links for those are down below or in the chat. And with that said, we'll see you next week.